So think about when we talk about probabilities, we're talking about basically, what are the chances that some event will happen? Look at that, you got your marks today. Yay. Telling you, it makes life easier. So here we're actually talking about, something very simple. We're talking about, okay, what if we flip a coin 100 times and basically calculate or compute the proportion of heads observed after each toss of the coin. So we know, when you toss a coin, you have either a head or a tail that you're going to land on, right? So we're talking about basically what is the proportion of heads that you will get in these 100 tosses. So they're kind of walking you through the experiment a little bit. They're saying, okay, the first flip, you ended up with the tail. So that means you got 0 heads because, the idea is we're looking at the number of heads here. So since you did not get a head, you got a tail. They're writing that as 0 out of 1 because you did one flip, you got no heads, so that's a 0. So that's a proportion of 0, 0 divided by 1. On the second flip, you get a head. So now we flipped our coin 2 times. So that's where you will see in that fraction, that denominator changed to 2 because you flipped it 2 times. And out of those 2 flips, one of them happened to be a head, right? So that's 1 out of 2, which is, of course, 0.5. We flip the coin the third time, it also lands on the head. So this time we flip the coin 3 times, and out of those 3, we ended up with 2 heads. So your probability has now changed from 0.5 to 2/3, which is 0.66666 repeating. And you can go on. So you can see how they actually graph this on this little chart over here to show you what those probabilities are going to end up looking like. So plot the proportion of heads versus the number of flips to obtain the graph, and we repeat this experiment to show you, next time when you do those 100 flips, what it might look like. So look at the x-axis. The x-axis is the number of flips, so that should be from 0 to 100. And on the y-axis, you have what that proportion will be. Like you saw, we changed from 0.5 to 0.667. So you can see sometimes the proportion goes up, sometimes it goes down. It's never going to stay the same, as you repeat both the experiments over here. It's always going to end up being different. So the idea here is, this is talking about short-term flips because we're only doing, 100 flips over, 2 experiments basically. And the observed proportion of heads is different and unpredictable for each experiment. And again, you can see those 2 graphs look obviously different from each other. As the number of flips increases, which means you do more than 100 flips, so as the number of flips increases, both graphs will actually start going towards a proportion of 0.5. So the more flips you do, that proportion actually starts evening out, because what they will say is half the time you're going to land on the head, half the time you're going to land on the tail. So that proportion actually starts to trend towards that proportion of 0.5. This is basically how probabilities work. So we're saying probability is the measure of the likelihood of a random phenomenon or a chance behavior occurring. So we basically want to know, what is the chance? What's the term they use? The likelihood that a certain event will happen. So here we're talking about coin flips, but you can think about, I don't know, not to create any political upheaval, but we know we're going towards a presidential election, right? And we have 2 main candidates that every news source is talking about. Whether we like them or not, or we support them or not, is different. But we can talk about chances, right? We can say, what are the chances that the Democratic candidate will win, or what are the chances that the Republican candidate will win, right? So again, we talk about chances. That's a probability there, basically. And of course, that is a much more complex calculation than just talking about coin flips over here. But that's kind of what we're talking about. What's the likelihood, or what's the chance that something will happen? That's what a probability is in its simplest terms. So it deals with experiments that yield random short-term results, or outcomes as they are called. But basically, they can help you reveal a long-term predictability. So you can actually do that on a longer term. So the long-term proportion in which a certain outcome is observed is that probability that we're talking about. So in this example, the probability of observing a head was 1/2 or 50%. That does not mean that, if we just stick with the 100 flips, that does not mean you got exactly 50 heads and 50 tails, right? We're just saying it's trending towards that. So maybe you had 45 tails and 55 heads, right? Not exactly 0.5, but at least we were getting closer to that probability. And as they were saying, the more flips we can do, the larger that number will be, the more even out it's going to get, and you're going to get closer to that 0.5. So that's actually that concept behind the law of large numbers is the more experiments we can do, the closer you should reach that expected probability that we have. Now, a coin flip is pretty obvious that it is going to be a 0.5 probability because you only have two outcomes. You can either land on the head or you can land on a tail. So that's two outcomes. One of them is a head, one of them is a tail. So each probability is actually going to be 0.5 when you talk about a flipping of a coin. Just your definition for law of large numbers: as the number of repetitions of a probability experiment increase, that proportion with which a certain outcome is observed, gets closer to the probability of the outcome. So in this case, again, with a flip of coin, we would expect it to be at 0.5. When you're talking about an experiment, we're basically saying it is any process with uncertain results that can be repeated. So flipping a coin would be considered an experiment. And we're actually going to be doing our own experiment once we get into chapter 6 to try and see how, some of these numbers would affect us. There was an example here that I wanted to talk about. Yeah. So right over here, we're talking about an insurance company cannot know whether a particular 16-year-old driver will have an accident over the course of a year. However, they are going to use historical records, and based on that, the company can be fairly certain that about 3 out of every 10 16-year-old male drivers will have a traffic accident during the course of a year, right? So they're using that historical data, which is kind of like their experiments, but they're not like putting 16-year-old drivers in situations. They're just looking at, how many 16-year-olds went and got themselves into an accident maybe in the first year of getting their vehicle or their insurance or whatever the case might be. So therefore, of the 825,000 male 16-year-old drivers, and again, those 825,000 become your experiments, the repetitions as they're saying. The insurance company is fairly confident that about 30% or 247,500 will have an accident. So what this probability does, it helps them determine what that insurance premium is going to be, right? How much the insurance rates are going to be for these, 16-year-old male drivers. Now that of course applies to all of them, right? They're not just going to single out those 247,500 people. All the 825,000 16-year-olds are going to be charged whatever that insurance rate will be, because they're saying, there's a good chance 30% of these people are going to end up in a accident, and of course the insurance has to pay that. So again, guys, just some terminology to be familiar with. When we talk about a sample space, that's the probability experiment where you are, collecting all the possible outcomes. So in the flip of a coin, your sample space will have two outcomes, right? Because you can only land on a head or a tail. Think about a is it six-faced or six-sided, I guess? Six-sided dice. Yeah. You would have six outcomes, right? The numbers 1 through 6. If we talk about a deck of cards, how many cards do we have in a deck of cards? 52. So each one of those cards becomes your sample space. So depending on what the experiment is, that sample space is going to change based on what are the possible outcomes. If we again go back to our election example, we know the presidential election comes down to 2 parties, right? I know we've had independents run, but usually by the time we get to that final stage, we usually just come down to 2 people. So then your sample space would be who's the candidate from the Democratic Party, who's the candidate from the Republican Party, right? So you would again only end up with 2 people in that presidential election. Your event is any collection of outcomes from a probability experiment. So basically what you can think about is, all the possible outcomes we have in the sample space. If we take one of those, then that would be considered an event. So an event consists of one or more than one outcome. Again, it depends on what the experiment is and what you're working with. We will denote events with one outcomes, sometimes called as simple events, because you only have, one outcome in there. In general, events are denoted using the capital letters such as E, and they had a little simple terms over here where they're saying an outcome is the result of one trial of a probability experiment. So if I tossed a coin, whatever outcome I came up with, that would be, the result from that trial. A sample space is a list of all possible results of a probability experiment. So let's take a look at this dial. This is talking about a fair die. When we say a fair die, what do we mean by fair? It's not created in one direction. Very good. So it's going to have an equal chance of landing on any of the numbers. If you guys have seen, and I know this movie was probably pre your time, but it's one of those Ocean 11, 12, 13, one of those movies where the guys go to Mexico. Ocean 8. Was it with the Ocean 8 also? Okay, this is the one with the men. They go to this factory in Mexico, they put this special metal in the dice manufacturing. So when they get those dice to the casino, I guess they're magnetically controlled or something, and they can flip it to win, whatever number they wanted. So those wouldn't be considered fair die, right? A fair would be, it has the same chance of landing on any one of those 6 numbers, is basically what you have.
In plastic dice, they can sometimes get bubbles on one side of the dice,
Yeah.
and then they will light on the side.
I mean, it really comes down to, how they make those indentations to put the holes for the 6 numbers in there. Even if one of those is incorrectly curved or carved.
Screw can sometimes lead to inaccuracies.
Yep. I mean, something as simple as that. So let's say we're rolling a fair die here. So identify the possible outcomes. So the idea is, if you are rolling a 6-sided die, your outcomes would be 1, 2, 3, 4, 5, 6, right? Those would be your possible outcomes, which means your sample space would then be a space with all those numbers. Now this one here, guys, we are using set notation. So if that is something you're not familiar with, then just remember, we use curly brackets to write all the possible outcomes, and that becomes your sample space. And then they're talking about an event. Now remember, an event can be one single outcome or it can be more than one outcome. So here when we're talking about defining the event roll and even number, well, there are 3 even numbers in here, right? 2, 4, and 6. So your event E will have all 3 of this. So this would not be considered a simple event. Remember, simple event was if you only had 1 outcome. This guy, of course, has 3. But so an event, remember, can have more than 1 outcome. It doesn't just have to be 1. All right, we'll pick up some examples from the section in the back, but let's talk about some rules over here. So if you're talking about the probability of any event, and that can be that event where you end up with an even number when you roll a die, the probability of that event cannot be less than 0, and it cannot be, it cannot be less than 0 and it cannot be greater than 1. So basically it has to be between 0 and 1, and it can obviously be equal to 0 or it can be equal to 1, but just nothing less than that or nothing more than that. It has to stay within that range of 0 to 1, including 0 or 1. The other rule you have to keep in mind is that the sum of your probabilities for all outcomes has to equal 1, because that means you're talking about 100% chance of something happening. So if you say 1, that is basically the decimal conversion of 100%. If you say 0, that's basically 0%. And of course, as a decimal conversion of 0% also. So they're basically saying if you have multiple events, forming up your, for your outcomes, when you add all of those probabilities together, it should add up to 1. It should not be greater or, for that matter, less than. So look at this example. So the color of a plain M&M milk chocolate candy, and of course, since we did this earlier in the year, we know it can be any of these, this is the standard milk chocolate candy, brown, yellow, red, blue, orange, green. Suppose a candy is randomly selected from a bag. Based on each color, it shows the probability. So if you have one bag, you can see what the different probabilities came out to be. But remember, this is based on that one bag, right? If you still again did the law of large numbers, maybe these probabilities would change. And I honestly think M&M does have an algorithm of how many colors they put in their bags of candy. All right, so to verify those rules for the probability model, you can see each of these are what we would consider as outcomes. You can see each of these probabilities are between 0 and 1, right? Nothing smaller than 0, nothing greater than 1. And look what happens when we add all of these probabilities together. It adds up to 1. So that's what they're talking about for your entire probability sample space. Your total probability must equal 1. It cannot be greater. So if you have any event with 0 as your probability, that actually means that event is impossible, which means it can never occur. If you have a probability of an event which is 1, then we are saying that's 100%, which means that probability is a certainty. It will most definitely happen. So if a probability is 0, it makes it an impossible event. If a probability is 1, it makes it a certain event, or certainty as they call it. Alrighty, guys, let's pick an example. Do a little bit of practice with this. Sorry?
I'm not like playing on my phone, I'm just verifying my things, so it'll not throw it.
Oh my God, where are you? All right, look at this guy. That's great. So remember how we were saying your probability can be equal to 0, greater than 0, as long as it is between 0 and 1 for each event. It can be equal to 0 or equal to 1, but just nothing beyond that. So this one is kind of interesting because apparently this bag of M&M milk chocolate only had one color. I've never seen that happen, so.
I see them in specialty bags, like,
Just one color?
Normal bag of M&Ms, one color, all yellow.
I guess I don't eat enough M&Ms.
I don't actually like M&Ms,
Yeah, I
but
like
like, I
peanut.
don't.
So obviously you can see this still satisfies our probability rules, right? Because each of the individual probabilities are between 0 and 1, including those numbers. And then when I add the total, I still get 1, right? Now, what can you say about this guy over here? This one is talking about verify, this is number 7. Verify that the table in the next column is a probability model. What do we call the outcome? Because it has 0, it's an impossible event. Yeah, very nice. Now, if we add those numbers, are they adding up to 1? Yeah. 15 and 15 is 30, so that's 0.2,
Oh,
0.3 is 0.6,
there's-
0.2, 0.2, yeah, 6, 7, 8, 9, 10. Let's see if we can find an example which maybe does not. Ah, nice. I just had to speak and here it is. So 9 and 10, why are they not a probability model? What's wrong with 9? Very nice, the negative. Because again, you can only be between 0 and 1. And you can see for the green color, it's telling us it's a negative 0.3 probability. So it fails right there. You cannot have a negative. But I would then imagine it's probably not adding up to 1 also. 3, 4, 5, 6, 7, 8, 9, yeah. And that's not even taking the negative into consideration. What's wrong with number 10? It's not coming out to be a total of 1, right?
Yeah,
Because it's
so-
actually 4, 5, 6, 7, 8, 9, 10. And then that's 1 and 2, so 1.2 actually, the total. So this guy is not adding up to just 1. So remember again, those two may seem like the simplest of rules, but they are very crucial when you're working with probabilities. True 40.
Wait, what page are you referring to? Hold on.
Yeah, simple, yeah.
230, try that one. It's the last one that I remember. My brain lost track of what you were talking about.
My brain is completely lost track, so it's okay. Just another definition here, guys. The unusual event is basically kind of in between the impossible and the certainty, because this one would have a low probability of occurring. So usually when we talk about unusual events, we're talking between 0 and 0.5. So kind of in that lower half of the probabilities is where we would say the unusual is happening. This one is saying typically an event with a probability of less than 0.05. So that's a probability of 5% is considered unusual. So they're actually going even smaller than what I would normally consider as unusual. So anything that would have a probability of less than 0.05 would be considered an unusual. So again, it's not likely to occur because we're saying its chances are very low. So just some terminologies to kind of keep track of. Alrighty, let's talk about how we can compute some of these probabilities. There's some more kind of explanation they're going through here in that paragraph that you guys can look through. But talking about using the empirical method, so this is actually based on observation, not so much as, well, actually, this can also be based on historical data, now that I'm thinking about it. So probabilities deal with the likelihood that a particular outcome will be observed. So we are talking about the idea of using relative frequency here. Probabilities computed in this manner rely on empirical evidence, that is evidence based on outcomes by doing an experiment. So probability of an event, so E, again, capital E for the event, is approximately the number of times event E is observed, and you're dividing it by the number of repetitions of your experiment. So let's take a look at how that would actually look in practice. An insurance agent currently insures 182 teenage drivers, and these are ages 16 to 19. Last year, 24 of the teenagers had to file a claim on their auto policy. So based on this, the probability that a teenager will file a claim for his or her auto policy is going to be based on, out of the 182, 24 applied. So that would be 24 out of 182, right? So the number of repetitions in this case was basically how many teenagers he was insuring, right? And then the outcome, what did they call it? Frequency of that event would become your, yeah, so that becomes the number of times your event is observed. So just some terminology, right? We didn't actually observe 24 people filing. They're just telling us 24 of these 182 teenage drivers filed. The auto policy. So that becomes the number of times the event is observed. And then the number of repetitions in this case happens to be how many total teenagers he was insured. So I guess you kind of have to think about in terms of what applies where, right? I mean, you're not again observing an experiment being performed, but how does that translate when we're doing these probabilities? Let's look at. So let's take a look at this guy. So we've got some table over here with information, and looks like we're actually looking at table 2 right now. Is the result of a survey in which 200 people were asked their means of travel to work. So we're talking about driving alone, carpools, public transportation, walking, maybe some other method of getting there, and working from home. So use the survey data to build a probability model for means of travel to work. So of course, when you add the frequency column, right, that's going to give you your total number of people surveyed, which is the 200. So that actually becomes your repetition, your total number of experiments that are happening. And then if we wanted to know what is the probability that people are driving alone to work, that would be what? 153 out of the 200, right? Which will end up giving you that probability of 0.765. And you guys can just plug that in your calculator quickly to get that number. And that's basically the same thing you're going to do. You're going to take 22 divided by 200 to get the carpool probability, the public transportation, same thing, 10 divided by 200. And you can see these single digits are really small probabilities because you're dividing by such a large number, a base of 200. Look at that last one is just coming out to be 0.035, or the one above it, 0.015. That's like what? 1.5%? Man, I'm just willy-nilly talking everything. But you will see each one of these probabilities are between 0 and 1. Now, can you tell me if we add up all of these, does it add up to 1? Can we verify that?
Table 3.
Table 3. Yes. Yeah. That would be 20. So 2, 5, 8, 10. So yeah, that's 20. Take back 2. So 7, 8, 9, 10. Yeah. To 1.000. So again, satisfies our probability model, right? All right. Okay, let's look at number 15. What would you guys say about it? Suppose that you toss a coin 100 times, you get 95 heads and of course 5 tails. Based on these results, what is the estimated probability that the next flip results in a head? So what would that probability come up to?
First part, because I know you say 2 different things, it's still 5, but we go off all those numbers.
So we're only interested in a head, right? Because they're saying if the next flip results in a head, so you're only looking at the total number of experiments, the repetitions would be 100, right? And then how many heads did we get out of those 100s?
5.
So using that, what would our probability of landing a head look? Yeah. Because of course they made it pretty simple in this one. So if we would say, what is the probability of getting a head? And I'm just using age to represent the head. That would be 95 out of 100. which like you said is 99%, or as a decimal, 0.9, right? So if that is your probability, then the next time you flip ahead, your probability would be 0.95, because that's what we're getting based on our observation, right? So that would be our empirical. This one here, number 16, is talking about the roll of a die, and again, they're shaking with 100 times, and you get 680 of those times. So they're saying, based on this result, what is the estimated probability that the next roll also results in 6? So what would that probability look like of landing on 6? Because again, they kept it out of 100, right? So it would be 80% or 0.80. So that's kind of what we mean by that empirical results, using them to come up with, because they're giving you all the information here. Yeah, I mean, honestly, putting that observable repetitions at 100 makes the calculation very easy. All right, let's take a look at 17 here. So they're saying Bob is asked to construct a probability model for rolling a pair of fair dice. He lists the outcomes as, and you can see it's going all the way from 2 to 12. Because there are 11 outcomes, he reasoned the probability of rolling a 2 must be 1 out of 11. What is wrong with Bob's reason? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, he's listed 11 numbers there.
Oh, I understand.
Because they're talking
Yeah,
about
I see.
these outcomes that he has. to
Yeah,
say.
I realized that.
Okay,
Forget that.
so he's rolling a pair of fair dice, so a pair tells you what? 2 dice, 2 dice. Because there are 11 outcomes, he reasoned that a probability of rolling a 2 must be 1 out of 11. What's wrong here? I want you to think about what are those outcomes telling you, because if you're rolling a pair of fair dice, technically, yeah, but if you're going to be rolling them at the same time, which is what I'm guessing he's doing, because they're telling you he's rolling a pair instead of 1 at a time, you do want to consider them together.
So it would be 2 out of 11 instead of 1 out of 11?
Got it, really.
Okay,
That makes sense. Yeah, I see it, I just.
okay, well, think about it. Because when you're getting a 2 from a pair of dice, what does that actually mean?
2 ones.
Yeah, because each of them will have a 1 and a 1, right? So this is actually the total that you are getting from rolling the 2 dice, because if you had, which you basically call as snake eyes, right? When you get those 2, that means you're adding 1 plus 1 to get the total of 2. So that's where that 12 comes from, right? Because if both land on 6, it's 6 plus 6, which gives you 12. So the idea is he's saying the probability of rolling a 2. What do we mean by rolling a 2? Because yeah, it could be 1 and 1 on both dice. Or is he talking about 2, like 2 on each dice?
Oh, it's weird
That
wording.
could be 4,
Okay.
right? I mean,
Yeah.
total of 4,
Yeah.
because you could be getting a sum of 2, or you could be 2 on each individual dice. So first of all, I think there's a problem with that description. And what's wrong with the 1 out of 11 then?
Should be out of 12. Or wait, that's what I said the first time too.
That's
I
what I
don't
was
know.
thinking at first, but I was like, no.
No, you have 11 outcomes.
It's 11.
Well, the list doesn't start with 1.
Because you wouldn't, right? Because if you're rolling both die, the minimum you can get on both is 1, right? You cannot get like 1 but 0 on the other one, because it's gonna land on some number. Because you always go from 1 through 6, so you will actually have 11 outcomes. I think the incorrect part is, they're talking about rolling a 2, but is it a total of 2 or is it on each dice? Being the 2, because then that could technically mean you can get a total of 2 or a 4.
So
Right?
there would be technically 2 out of
2 out of this, because there's 2 outcomes that get satisfied. So yeah, you gotta be very careful with your
Would
language.
it also be 3 outcomes? Because if you're just saying rolling a 2, it just says A2, not a pair of 2s. So you can actually have 1, 2, 2 2s or equal to. It just says roll a 2.
Yeah,
So
so wouldn't that
I
be,
can roll a 2 and a 6, or I can roll 2 2s or.
oh, so you're saying if one single die
Plus 1, so it could be 3.
also lands on 2?
Yeah.
Yeah, so then you can have multiple options then. So Bob doesn't know. what he's-
Sorry.
Bob, we don't even know him and we're calling him a junkie.
Yes.
Jeez, sorry, Mom. All right, guys, let's talk about classical method. So this one actually is talking about when each outcome has the same probability of happening or the same chance of occurring. So you will see here, we're talking about second line. The classical method does not require that a probability experiment should actually be performed. It relies on counting techniques. So we are saying the classical method requires equally likely outcomes. When we say an experiment has equally likely outcomes, we're saying they have the same chance of occurring. So going back to our point here, you can land, there are 2 outcomes. You can either land on the head or a tail. So our total would be divided by 2. If I land on the head, that's 1 out of 2. If I land on the tail, it's 1 out of 2. So either of those outcomes have the same chance of happening, right? Because that's a 50-50 chance. That would be equally likely outcome. For that matter, even with the dice that we're talking about, a fair dice is plural, right? Die is singular. So these are the 6 outcomes that we can have if we're looking at a 6-sided die. So if I talk about, okay, what's the probability when I roll my die, it's going to land on them? Well, that's going to be 1 out of 6. But that's going to be the same for 2 also, right? It's going to be 1 out of 6 because 2 is just 1 event out of 6 total. So even with rolling of a die, you have equally likely outcomes. So that's kind of what we're talking about. Each event will have the same chance of occurring. And I think they're talking about that experiment right over here. So when we're talking about our probabilities using the classical method, let's clear this out. We're basically saying if you have an experiment that has n equally likely outcomes, and if the number of ways that an event can occur is m, then we're basically saying the probability of this event happening is going to be m divided by n. So how many times can that event occur divided by the total number of possible outcomes? So they're kind of getting a little too technical here with the terminology or the notation, but this is basically saying the number of times that capital N represents how many times. So the number of times event E happens divided by the number of outcomes you have in your sample space. So how many numbers are in your event? How many numbers are in your sample space? So let's take a look at this guy here. And you can see they are going with a pair of rolled fair dice being rolled. So here we're saying fair die are die when each outcome is equally likely. We talked about that. What is the probability of rolling a 7? And I love that they give you this visual representation here because you can have a total of 36 equally likely outcomes. So that was also another thing that was wrong with Bob because he went with the most simplistic of options. He just said 11, but look at, then this is Drew kind of what you were talking about because you can have a total of 2 or you can have, individuals landing on 2 or we can have both of them landing on 2, right? So the first thing was all he did, and I'm going back to Bob here. Junkie Bob. He just added, like, if you added those numbers, what you would come up with, right? But he didn't consider the different combinations. So instead of 11 outcomes, you actually have 36 outcomes. You cannot simplify the sample space just based on, oh, if I add the numbers, what does it come out to be? Because there are two different ways you can get a 3, right? If the first die lands on 2, the second on 1, or the first and the second are, or look at the number of ways you can get a total of 4. You can get 3 and 1, 2 and 2, or 1 and 3, right? So he had simplified those outcomes too much. So first there was ambiguity because they were not talking about what those outcomes were. So they didn't specifically say you were adding those numbers. That's an assumption we made just by looking at the totals. And then they ignored all the multiple times those events can happen. All right, so what is the probability of rolling a 7? So all of these 36 become our sample space, our total number of n values for the sample space. How many of these add up to a 7? So how many times can we get 7?
Three or six. They're in the red, are they not?
They are in the red, yeah. So you can see that's a total of 7, 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. So that's 1, 2, 3, 4, 5, 6, right? So out of 36, 6 of them are a total of 7. So you are getting probability of rolling a 7. It's going to be 6 out of 36, which we could reduce down to what? Yeah, you are working with fractions, so you will need to reduce the fractions down to simpler terms. I know. Welcome to math. You guys have enjoyed non-math statistics so far.
Math in my math, disgusting. 0.16.
Okay, change that to a fraction.
Oh, 6.
Yeah, because 6, divide 36 by 6, you're going to get 6, right?
Yeah.
So 6 goes into itself, so you know when you're dividing, 6 goes into itself once, goes into 36 6 times, so that fraction becomes.
Oh.
And you know, when in doubt, I'll show you on Desmos if I can actually get this thing to work. Buddy, flip page. Okay. I don't know if we'll find it handy or not, but Desmos just introduced their 3D calculator. So this is what you had, right? And if you go to Desmos, and I'm showing you on Desmos because it's really simple, just click on that fraction and then converts it. Isn't it? We did not grow up with this technology, people. You guys are very lucky. So it becomes 1/6. Okay, so they want to know what is the probability of rolling snake eyes?
So double the same number.
So probability of rolling a 2.
Oh, it's you. One.
How many snake eyes do we have in the out of 36? Yeah, very
One.
nice, just this guy. So this would be the probability of rolling a 2 would just be 1 out of 36, and of course we wouldn't be able to reduce this. Comment on the likelihood of rolling a 7 versus rolling a 2. So remember this guy was 1 out of 6, or 6 out of 36. Which is, I guess, more likely to happen easily. Would you be easily getting a snake eyes, or would you have a better chance of getting a 7? And why is that?
Because there's more possibilities to roll a 7 than there is stays.
Yeah, because you only have one outcome out of 36. And remember how they were talking about if your probability is less than 0.05, that's when we call it, what did they call it? Unlikely or unusual? I think they said unusual event, wasn't it?
Yeah.
Yeah, we just talked about it 2 minutes ago. Anyway, it's one of those events that will more than likely not happen. So that's what the 1 out of 36 tells us. Even though 6 out of 36 is pretty low, it's still better than the 1 out of 36, right? Because like you said, you have a few more options of landing a 7 than we do with the 2. So that's telling you based on the probability, because that 1 out of 36 is such a small number. And you know, if it helps, convert them into decimals, because decimals are easy to compare.
I want to do an exercise in regards to dice anytime soon. I have an entirely bag of dice.
Oh, really?
It's pretty deep, so if you need them, let me know.
Right, that might be fun. Yeah, we can try that. So are they showing us decimals? No, and just to show you how they are writing out those outcomes here, guys, look at the example for the 7. So based on where the dice lands, 1,6 is not the same as 6,1. Yes, it's giving us the same result, but the idea is here, the first die landed on 1 and the second on 6, right?
I want a night.
So yeah, it really does make a difference on which die gave you what number. So, and that's kind of what, again, our junkie Bob did, was he just took all of these and called this whole thing one outcome of 7, right? He just placed all those options, just condensed them into one, which is where he also went wrong. So those are some things, you know, as you guys will start going through examples and designing your sample spaces, you will need to keep that in mind. All right, so this one is a little bit different. This one here, we're talking about Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all want to go to the concert with her. So to be fair, Sophia randomly selects 2 people who can go with her. I guess she's got to keep 1 ticket for herself, right?
Yeah.
All right, so determine the sample space of the experiment. In other words, list all possible random samples of size 2. So what we're basically saying, she has 4 friends, but she can only take 2 of them with her, right? So you have to come up with all the different combinations of what that sample space would look like. So kind of like we were doing with the pair of dice, she can obviously take Yolanda and Michael, right? Or she can take Yolanda with Kevin, Yolanda with Marissa, right? And then you have to keep changing that. Now, will Yolanda and Michael and Yolanda be the same outcome? So if we did Michael and Yolanda, would this 2 be considered different outcomes? Not in this example. That's kind of what I'm.
It's the same kind of, like you can't
Still
really.
the same pair of people, just doesn't matter who you asked first or second. So Michael and Yolanda's already been taken care of, which means we can do then Michael and Kevin, and we can do Michael and Marissa. Okay, what other combinations? We already got Kevin with Yolanda, we've got Kevin with Michael, Kevin with Marissa. Okay, and then Marissa with Yolanda, Marissa with Michael, Marissa with Kevin, so that's it. 1, 2, 3, 4, 5, 6. All right, let's verify that. 6 outcomes. Okay, looking at that table 4. Okay, then they are asking us, compute the probability of the event Michael and Kevin attend the concert. So what kind of probability can we place on Michael and Kevin? Which was our MK option in the stack. Well, probability's got to be a fraction. Very good, because there was only 1 outcome where Michael and Kevin, get to go, so that would end up becoming 1 out of 6. All right. Probability that Marissa attends the concert. So what this means is she is one of the people, it doesn't matter who the other person was. So what would that probability come out looking like?
6 or 1/3 or 1.
So how many outcomes was Marissa attending the concert? 3, because Marissa was the MA, right? So that's 1, 2, 3. So that's going to be 3 out of 6, or like you said, what was your short simplified? Yeah, very good. So 3 out of 6, which is the same as 1/2. Interpret the probability in part C. So what does that tell us about Marissa's chances of attending the concert? It's gonna be half, right? Because how many times can Kevin go to the concert if we just did Kevin by himself? Yeah, because he's in 3 events too, right? There's the Kevin Man, I feel like I'm talking about him. So 3 events with Kevin. How many events with just Michael? He's just the M? So 3 for Michael and Yolanda? 3 as well. So actually, all 4 of the friends have 1/2 of a probability being selected. So that's good, right? Because then I guess neither one of them can say, hey, you favored this person over me, because each one of them had 3 out of 6 chances of being selected. All right, awesome job. Thanks. Let's see if we can go to example number 5. So 230. That was 240. It's not the probability part. This one is just having us design the sample space, but they're saying if a person rolls a 6-sided die and then flips a coin, describe the sample space of the possible. Oh, we may not have talked about this one yet. Because you're doing one thing first. And then okay, we'll come back. Yeah, because this one. Thank you. Thank you. #31 roulette. So in the game of roulette, a wheel consists of 38 slots numbered from 0, 0, 0, and then of course 1 through 36. To play the game, a metal ball is spun around the wheel and is allowed to fall into one of the numbered slots. Now, the idea is it should be fair, and it should have an equal chance of landing in any one of those slots. So what would your sample space be?
Those 30.
38.
You should have all those 38 numbers in there, right? So if we have to list this out, which we're not going to, because it's tedious, but the sample space would start with 0, 0, 0, and then you would do 1, 2, 3, 4, all the way through 36, right? List all of them. So what is the probability that the metal ball falls into the slot marked 8? Okay, so there's the 8 right there in the top left corner. Yeah, 1 out of 38, right? Because there's only one slot which is marked with number 8. So the probability that the metal ball will fall into 8 is going to be 1 out of 38. What is the probability that the metal ball lands in an odd slot? Now this one we'll need to think, because how many odd numbers are there?
My brain's not working, it's just divided by 36, it's the 2 and the.
The 0 zeros wouldn't count.
Yeah, so it's out of 36, my brain's.
Half 36, because half of those are those 2.
If it's 2 through 36, of course, all of those numbers would be even, 1 through 35, so it should be. We will trust our math here, people, because I'm not gonna.
Right, separate.
Can I use that excuse?
Yeah.
So 15 out of what? sorry. 18. It's his fault. He said brain's not working and mine stopped working.
I'm sorry.
18 out of 38 still.
Yeah, you still have to do out of 38. because-
Yeah, you still gotta do it out there.
So what will that reduced fraction look like?
It's 1/2.
No, 18 out of 38 is not one.
Wait, no,
half.
hold on, wait, no. I'm on brain. I'm on brain. Oh, wait, no, Mark. Do the thing, stop it.
I need a
She already did
fraction. 15 out of 38. Oh, I'm just leaving
Oh.
it as a decimal. I need a fraction.
That's fine, you can do it.
No.
That's correct, it's fine. I'm gonna have to do it just the same as what you're gonna have to do.
Okay.
Yeah, in second fractions.
19 people because 2 goes into both of them. So we will obviously have better chances of landing in an odd slot than just the 8, right? Because that has a better probability. Okay. Because I think the other ones were more like empirical because they're going with, observable answers here. All right, what page were we on? 35?
235.
Thank you.
I was thinking that's simple too. Through that. I used to work at a casino.
Oh, you
Oh,
did?
wow, yeah. There's many more ways, it's not just one to win. If your answer would have been probably a win,
It would be very different, yeah.
very different, because you win like, I think 4 or 5
Oh, okay.
times. Really good.
I do not gamble, people. I work very hard to earn my money. So yeah.
Play lottery.
Oh, is it?
After working at a casino.
Okay. Okay. Well, I haven't won any of those big mega, billion, trillion, whatever they went into one of those. All right, guys, let's see a comparison between the classical and empirical methods. So here saying, suppose that a survey asked 500 families with 3 children to disclose the gender of their children, and they found that 180 of the families had 2 boys and 1 girl. So in this case, they're saying, okay, estimate the probability of having 2 boys and 1 girl in a 3-child family using the empirical method. So of course, remember, empirical is based on the observations. So that would be a total of 500. Out of that, 180 have, this combination of 2 boys, 1 girl. So that would be the 180 over 500, which of course comes out to be a decimal of 0.36. So we're saying that's about a 36% chance that you would end up with this combination of children, right? 2 boys and 1 girl. But what if we wanted to compute and interpret the probability of that same combination using the classical method, assuming that boys and girls are equally likely, which it is, right? I mean, if you think about, a pregnant person, are they going to have a boy or a girl? It's going to be 2 outcomes, kind of like our flipping of the coin with a head or a tail. Because those, again, we're kind of staying with those standard gender definitions here, boy, girl, 2 options, you get one or the other, that's 1 over 2, 0.5, equally likely chances. So that's what they're kind of using as the idea over here. But look at what a classical example would look like. So this is what we would call as a plum saying tree diagram. And this is actually what we need to use when we do that number 19 example that I wanted to do with the die and the coin flip. You have to first come up with your sample space. So we start by each event, what the outcome will be, and build up from there. So you start out with the first time the parent has a child, right? So the first time they have a child, their option will only be either they have a boy or a girl. Now, let's say they had a boy and then they go on to their second child. Again, they have one option of boy and girl, but when they go to their third child, an option of boy and girl, right? So that was just this part. Whoa.
uses in genetics. Uses.
So they had a boy the first time, they had a boy second time, and boy the third time, which gets us to 3 boys, right? But what if instead of having a boy for the third time, they ended up with a girl, so which would bring them to this combination. However, when they had their second child, what if they had a girl instead of a boy? So you wouldn't be going up to that top half of the tree, you'd be coming down here. So they had boy for the first time, girl, and then the third child would be again 2 options, right? Boy or girl, which will give you 2 more outcomes. So you have to go through each branch of that tree and figure out what the options would be. So same thing happens here. What if they had a girl the first time? So they can go to 2 options from there, 2 options from there, and you can see the other 4 remaining options. So out of these are 3 boys. There's a 2 boy, 1 girl option. I think that's boy, girl, boy. So that would again be 2 boys, 1 girl. 2 girls, 2 boys, 1 girl. 2 girls, 2 girls, 3 girls. So out of 8, 3 of them are going to be 2 boys and 1 girl, right? So what will 3 out of 8 look like as a decimal? Because remember, we got 0.36 as the probability from the observation. 0.37. So not too far off, right? Because it's pretty close, because if you're getting 0.37 and you had 0.36 from the first one, I mean, not too bad. We're still pretty close in the neighborhood of that probability. But obviously there's a difference, right? From the observation, because you had 180 out of 500 families who had 2 boys, 1 girl. And by the classical, you are ending up with 0.375, so slightly higher than the empirical. This one is talking about using simulation, but I was hoping to do. We'll come back to this. Let's go back to our tree diagram option here, because I do want to show you this. All right, let's come back to him. So we are talking about if the person starts out by rolling a 6-sided die first and then they flip a coin, what would your sample space look like? So let's do what? Okay, so what are the 6 possible outcomes we can get if we start by rolling out a die? 1 through 6. So first, roll of a die. So either of these 6 options you can land on, right? And then you are flipping a coin. So if we landed on a 1, then you would go into a head or a tail, right? So then that would lead you. So it's the same kind of thing with the boy girl, right? Each of the outcomes would then have to have either a head or a tail. Because you're tossing the coin second, flipping the coin second and rolling the die first. So what would our outcomes look like? Seriously?
Like the total probability you're.
Like the list of outcomes, what would that be? So if you start with the 1,
1 heads, your
1 tails, right?
So they'll each have 2.
So each of them you would then have to list it out. So how many total outcomes would we end up with in this sample space? So all of these together would make 18 or 12?
No, it would be 12 because it's just that.
So each get 2.
Yeah. So 12, right? So this would be the entire list of your sample space. I'm telling you guys, tree diagrams work out really well where you have multiple events happening one after the other. So like the 3 kids, or in this case, the roll of the dice first, and then the flip of a coin, and I'm gonna miss those out, but you get the idea, dice first and then the coin. So a tree diagram really helps you because you can visualize it and you can list it out. You will actually see, trying to think if this textbook had that example or not, but a lot of times they would do, like, if you have pair of pants, 5 shirts, 2 jackets, how many combinations of outfits you can create. So you will see examples like those where they'll give you they can do with menu options. You have 3 appetizers, 4 entrees, 2 desserts, 3 drinks, or whatever that may be. How many different meal combinations. So that's kind of where you would want to do the tree diagram. So you can kind of visualize and see what those were. Okay. All right, guys. So we'll pick up from here next time. I know it's after 3 o'clock. So Tuesday, the 10th, we are doing chapter 3 exam, and then we'll come next Thursday and pick up from here. All right, everybody, have a wonderful weekend. There's candy and some other stuff that Trio left that you guys can grab that.
And then I got help with the, I have to, I don't